I think we can get ready to start them. So, can you hear my voice and screen?
Yep.
Okay. So, welcome to our annual reading club. So, this event is hosted by Women in AI across different chapter. And my name is Sue. So, I'm from Women in AI Myanmar chapter, and I will be your host for today's session. So, to start off, let me give you a little bit background about our organization. So, Women in AI, we are a non-profit organization working to make AI more inclusive globally. So we are founded in 2016 with over 8,000 members in 140 countries, and we are still expanding much more. So this community is about women support other women to create a more empowering, inclusive, diverse network through hosting various types of events like the one you are joining today. So of course, each chapter run their own type or event in their local country. And then the next big one that is coming, and we are excited for it. It is the Women in AI Award, which will be taking place next year in June to celebrate some of the amazing achievement of women in STEM. So we hope to see you there. So feel free to become part of this amazing community by scanning the QR code in the left corner of this presentation. Please do not hesitate to reach out to us if you have any additional question or if you also like to become the volunteer like one of us. So this reading club is a series that has been running now for a few weeks. We are currently onto the week 6. So I would like to talk about a little bit recap about the week 1, which is about the keynote, and the week 2 is about zero-shot learning through cross-model transfer, and the week 3 is about introduction to ROC analysis, and the week 4 is presented on the adversarial AI class hardening design hardening, and week 5 is the learning from imbalanced data. So we are currently onto the week 6. Data. So Angie is a data scientist working at Commonwealth and Australia. So hi Angie.
Hi Sue. Hi everyone.
Yeah, are you ready to share your screen?
Yeah, I can get started.
Okay.
Sorry, I was just saying, let me know once you can see it.
Yes, it is okay. Yeah, you can start right now.
Okay. Awesome. All right, I believe you can all see my screen. Can you all hear me okay?
Sure, we can hear you.
Okay, great. So yeah, I guess before I start, I'll just a quick introduction. So I think Sue's already introduced, but just a quick introduction regardless. So I'm Angelica. I think a lot of people calls me Angie. So at the moment I'm working as a data scientist at Commonwealth Bank. I'm also very heavily involved with Women in AI with a couple of initiatives, being a survey analytics lead, and trying to initiate a couple of initiatives around APAC at the moment as well. So regarding the paper, I guess before I even kick off, it's been already kicked off in the last week, but given the length of it, I think it was partially completed. So I plan to cover the rest of the contest that wasn't completed. However, conscious that there could be attendees who hasn't probably made it in the past week, or even though if someone else have made it, I'll still do a quick recap of the ones that's already been covered and then move on to the next ones. So yeah, as you can see, the paper is called Learning from Imbalanced Data, and that's kind of pretty self-explanatory. Often we get data sets that are not balanced, which means that the target we are trying to predict, they will have examples, they will have an imbalance in examples. So if you want to, let's say, predict a yes or no, there would be, sometimes there are instances when there are only 10 no's, but hundreds of yeses. So that's when our models kind of struggle in giving a good accuracy of the prediction. And that's why some methods of tackling this problem exist. And this paper is, in my opinion, this paper is kind of a dictionary of procedures you can apply for tackling this problem, but it doesn't cover each of those topics at a great length in details, and which is why, just a point of caution, I may not go do a whole deep dive in a lot of topics that we're just going to skim through, which due to the nature of the paper. So before we even kick off, like I said, we're already kicking off, but couple of concepts that we need to be aware of while considering this paper is that this paper kind of goes through a data set which is a mammogram data set. In here, it contains majority class is the negative class in here, and by negative class it means that people don't have cancer. Positive in here is a minority class, which is much less in quantity, as you can see, only 260 out of 10, or out of almost 11,000. That is a positive class. Another thing I'll say is that I'll heavily cover contents from section 3 and 4 because 1 and 2 has already been covered. I'm just skimming through 1 and 2 before I go on to the next sections. But yeah, please feel free to stop me at any instance if you want to get some clarification on a specific topic. I guess I'm just going to the highlighted concepts. So in terms of imbalances, this paper has talked about 2 different types of imbalances. One is intrinsic, another one is extrinsic. And by intrinsic, it means that the imbalance is a direct result of the nature of the data space, meaning that if it is intrinsic, it is already embedded in the data set, and there's nothing we can do about changing the nature of the data set. Whereas in contrast, extrinsic could mean that there's failure in the process or some storage issues or some streaming issues, which could be solved, but because they were not fixed, because they were not that kind of control in place, that's why we are in an extrinsic data set, we have we are missing those negative samples that could otherwise have been in the data set originally. So there has been last week has been covered pretty in a big detail, and it's basically saying it's kind of in the highlighted area saying that this is actually procured from a continuous data stream of balanced data over a specific interval of time. And if during this interval, the transmission has a sporadic interruptions, and that's what I mean. So due to this interruption, if it wasn't there, otherwise, this data set probably wouldn't have been unbalanced. 2 more concepts that were covered are relative majority class. The unbalance in the data set is due to there's a relative in the majority class, and there is an absolute or rare instances in the imbalance in the majority class. So the relative instances are basically saying that, let's just read this a bit quickly. So it's saying that the minority class is still outnumbered in this case with only 2,000 examples. It's not necessarily rare in its own right, but sometimes what happens is that if you let's say there are 100 majority classes and 10 minority classes, if you double the number of majority classes, your minority classes would also increase by twofold, which is like there's a relative increase. That's why the relative, the notion of relative kind of exists in here. And the imbalances due to rare instances, which is in contrast to that, is a representative of domains where minority class examples are very limited, which is even if you increase the number of majority classes, chances are that those minority class examples may not increase proportionally because they're so rare that you can't really increase them. I don't think there's any other concepts that we need to be much aware of to carry on with the next few topics that were not covered last week. Just on that quickly. So it's basically talking about which has been covered. So in terms of tackling the problem of unbalanced data set, there are two techniques. I think the basic ones are the oversampling and undersampling. And if you want to, the oversampling happens is when you want to increase the number of the minority class so that your data set is balanced. And you all essentially what you're doing is just randomly picking, randomly kind of oversampling the minority class, like creating duplicates of those minority classes. And on the flip side, undersampling is basically you're just randomly picking some majority class examples and you're removing the rest of the examples that were not picked up by that random sampling. And there were some pros and cons that were mentioned here. I think there were videos on week 5 paper reading, so you can go through that, which was explained in a huge detail in there. After that, there has been some mention of informed undersampling. And in this case, informed it's not random. It's informed in a way that it is what it's trying to do is it's developing a learning system by independently sampling several subsets from the majority classes. So it's kind of independently sampling them, taking like different folds from the majority class, and then it is combining each of those subsets with the entire minority class, creating different models, and at the end combining all of those models. That's why it's called an ensemble. Then another thing is balanced cascade. The difference between this and that is that it's saying that it's a supervised learning algorithm that is kind of, it is also an ensembling in a way. But what it's doing is it's not just randomly selecting training data sets and randomly selecting majority samples and combining it with minority samples, whereas what it's doing is that it's iteratively adding majority samples with minority samples. So, and when it has added in the first instance the majority samples, it has already extracted information from that. So it is not considering it in the next update. So it's kind of sampling without replacement. And then it's doing it kind of sequentially. So that's why the mention of cascading exists. And k-nearest neighbor it was mentioned as well. Sorry, I'm just going through it a bit quickly only because it was mentioned. But k-nearest neighbor is just applying few techniques on kind of picking like you mentioned the k. If you specify 3, k as 3, then it's picking 3 nearest neighbor around the minority class and kind of picking those. And then based on specific criteria which are mentioned here. So there are 4 methods that has been applied pretty drastically out there. So near miss 1, there's near miss 2, 3, and there's most distant method. SMOT has been covered last week, but I'll probably just I'll go a bit more into depth on this because it actually is quite widely used in tackling this kind of problem. So SMOT, as you can say, it's just an abbreviation of synthetic minority oversampling technique and minority oversampling. So it is actually sampling the minority class. It is oversampling, not undersampling. So oversampling the minority class. But how is it doing it? So I will probably just do it on a notation basis because it's easy for me. S-min here, it is a minority class. It is the subset from the entire data set of those minority class examples initially that we mentioned. So those 260 minority class, S-min is equals actually 260. And for those subset of minority class, you're considering k-nearest neighbor for each of those minority class examples. So it is not the target. This is actually the independent variables for kind of predicting that minority class. So xi in here is that independent variable to predict the S-min, which is the minority class. What it's doing is that it is calculating. I'm just going to go through this formula first. So what it's trying to do is that for a dependent variable, it is looking at those, let's say, in this case, we have to specify the k. If we specify k as 6, it's looking at six of those neighbors close to it, taking a difference of the distance, then kind of tuning it with the hyperparameter, in this case, this delta hyperparameter, which is the value is between 0 to 1, which we specify in the model. We tune it. We time it by this, and then we add it to our example, like the point we chose in here, according to which we are calculating those k-nearest neighbor. And that example is our new synthetic sample. So that's the synthetic sample, which is fake. Obviously, it's not original data set, but the reason it's been done that way is to kind of oversample those instances of the minority class. And the reason why we do it is because it is kind of mentioned here. So why we do it is to kind of, again, it's not random. It is informed, but it's kind of a bit clever. It's adding noise to the data so that when there's a prediction you're doing, you can kind of predict those minority classes with a bit more generalization. Like you're not overfitting to the minority class that may exist when you're randomly oversampling it, which is like examples given here. So as you can see, this X new is essentially this little dot that's been created here. So this xi is here, as you can see. This xi hat, which is one of the nearest neighbor. So it's that, calculating the distance, tuning this distance by a delta, which you specify as a hyperparameter, and then you're adding it to the xi to find this distance. So that xi, the x new is there, but it's essentially here. Yeah, I'm just going through it quickly again. So again, the SMOT has problems. Obviously, it is, what happens is that if you add too much noise to the data, sometimes it is doing opposite of what overfitting does. Sometimes it is doing some underfitting, which is like generalizing it too much, like adding too much variance that you sometimes struggle to pick your minority samples, predicting minority samples with a bit more accuracy. So there's like a fine balance when you're using SMOT. You probably have to play with the K if you want to fine tune it to do your prediction, which is like how many nearest neighbor you want to choose. You can specify, like do some kind of grid search, or you play with delta or both, so that this case doesn't happen. All right. This one, okay, I'll just go through it quickly as well. Even though it is kind of used, so it's variants of this is used like AdaBoost, but this adaptive synthetic sampling kind of employs the concepts from SMOTE. So what it's doing is that in this case, it's just trying to kind of tackle the problem SMOTE has. So what SMOTE does is, again, it doesn't consider the neighborhood examples, like without actually considering how many neighbors you should choose, even though you can specify the K. It does it quite randomly still. And due to this, what happens is sometimes you can have an overlap between that. Imagine this is one of those synthetic samples, the star. It's not, but I'm saying that let's say it is. And it is kind of just being like, it is overlapping with the majority class sample. And when that happens, and then when you model on this data set, let's say classification model, if you employ one here, it won't be able to actually separate the majority from the minority class. And that's the problem that's happening here. So what this is trying to say is that so that this doesn't happen, you can apply either something called a borderline SMOTE or adaptive synthetic sampling. And let's just look at this borderline SMOTE a bit quickly. So what it's doing is that, again, it's employing the nearest neighbor concept from SMOTE again. So xi, which is, let's say you're randomly picking one of the examples of the independent variable that yields the minority class. And then for those independent variables, you again identify the nearest neighbors that are belonging to the majority class this time. So previously, you were taking the minority class examples. This time, you are identifying the number of nearest neighbors that are majority class examples. So this is basically what it's doing, is that it is essentially just picking those majority class examples, like it's taking an intersection between all the samples, let's say all the nearest neighbors, and the majority class example, the neighbors that are belong to the majority class examples. It's taking that and making sure that it is only taking that when the value is less than m or greater than m divided by 2. And in this case, I think I've said that what m here is the majority examples, so that it doesn't equal to m. It has to be less than m. It has to be less than the majority class examples. And briefly mention that if it is actually, if it somehow gets equal to m, all of these examples fall under the majority class examples. So you won't actually be able to pick up those minority class examples for this problem. And there's a visualization here, actually. So this is trying to say is that, let's quickly move here. So this is like the danger instances. So if you look at A, there's a synthetic instance that's been created for A here, but it is considered as the danger instance here because it represents a borderline minority class examples, because it probably could be misclassified in this case. Let's just go through this quickly as well. So a major difference between borderline SMOTE and SMOTE is that SMOTE so it's basically saying what's the difference. So it generates synthetic instances for each minority instances, whereas this borderline SMOTE only generates synthetic instances for those minority examples closer to the border. So yeah, as you can see, it is not like generating synthetic instances. Let's say there is no synthetic instance between these two stars, but there is one in between these two. In that case, it is actually not creating this extra noise that SMOTE creates. Okay, so okay, let's look at this again. So it's an adaptive synthetic boosting. It is adaptively creating different amounts of synthetic data according to the distribution. So what it's doing is essentially is that it is calculating the number of synthetic data examples that needs to be generated for the entire minority class. So what in here is that this is calculating the number of synthetic data examples. So we want to generate this many synthetic data. So the difference between how many majority class examples we have minus how many minority class examples we have times with a hyperparameter here, which you can tune. So like that's something you can play around with. It depends like how many synthetic data examples you want to generate. If you provide a higher value for this, you'll generate a lot more synthetic minority class data. If you provide less value, you will create less, obviously. Then what it does is that, so after that process, it is finding the k-nearest neighbor according to the Euclidean distance of the to calculate this ratio. So this gamma ratio, what it's doing is that this delta I is the majority class examples actually. So around that xi, which is the minority class examples independent variables, it is only picking those that are that fall in the majority class examples here. It's like it belongs to here. That is denoted by delta I in here. Then this k is the k nearest neighbor. So how many do you want to pick here? So let's say out of 6, you have 3 majority class examples and 3 minority class examples. So say k here is 6, delta I is 3. And what it's doing is that it's kind of just trying to normalize it so that this gamma falls between 0 to 1. Because it's a distribution, it's like a normal distribution. You want to have like the you want to have the values between 0 to 1. It's kind of a Gaussian curve here. So after this, it determines the number of synthetic data samples that needs to be generated for each xi belongs to S min. So with that calculation, it is timing it with this value. So remember, this is a value, like how many synthetic data we want. And we are adjusting it with this parameter that we calculated here. And this final value, this will be the number of synthetic data samples that will be generated. So that's just like the intermediate step, but this is the final step of generating how many data you want. Yeah, so it's basically ending here. And okay, so why it's done, right? So it's done because let's just read that. Sorry, I'm just going to read that quickly so I can explain it. So key idea of Addison algorithm is to use density distribution tau. Sorry, not tau, it's the gamma as a criterion to automatically decide if the number of synthetic samples that needs to be generated for each minority example is by adaptively changing the weight. So yeah, so it's basically trying to say is that you can adaptively change that at each iteration, so that you don't have that like the distribution that's one-sided. You can have like a very balanced distribution of majority and minority class. This was explained, I think, just very quickly. I'll go through this atomic link, and it's a data cleaning technique. It is always like, I think, what I will say is that I think I'll start from here because that wasn't covered. But yeah, just very quickly on this. Atomic link, it is, I think the best benefit you get from this is when you combine that with a SMOTE technique, which is this one. I think it's explained here. So when you apply SMOTE, I think we explain what SMOTE does. But after that, the atomic link is trying to link a majority and minority class examples that are very close to each other. So it's kind of trying to put them in the same cluster and checking which ones are the closest to one another. Whenever that happens, so the reason that's done is that, okay, there might be a chance that they are probably overlapping on each other, and you want to remove it from the data set so that when we are actually applying a model, it is able to draw a decision boundary easily so that our majority and minority class examples can be easily separated. And that is why this is done. Yeah, as you can see, it's saying here, this algorithm produces more well-defined class clusters, which potentially contributes to improved classification performance. So that's why it's done. So I think it's pretty good so the problem mode it can be alleviated by using atomic links as a data cleaning method. I'll just quickly check, just do a time check as well as check on the. I can't see the chat, but does anyone have any question at the moment? If not, I'll carry on.
Currently, no question, so you can carry on.
Yeah. Okay. Cool. I'll carry on because I think time passes pretty quickly. Even if I did a recap, I think I already lost 30 minutes. But yeah, sorry if I rush it. But yeah, just stop me again. Okay. So starting from here, cluster-based sampling method. Essentially, this cluster-based sampling method, all it's doing is just trying different variations of k-means clustering, different from k-nearest neighbor. So I hope you know this is an unsupervised technique. It is trying to iteratively kind of create different clusters to put them in different, to separate between positive and negative, or in a binary case, obviously, till all the data points are exhausted. Let's see how this is working for this kind of problem. So they're calling it a cluster-based oversampling algorithm, and it is effectively dealing with the within-class imbalance problem in tandem with the between-class imbalance problem. And I think it was mentioned last week. So between-class imbalance is the imbalance between the majority and minority class, and within-class imbalance is the imbalance when you have when it is within the class, let's say within the majority class, but there are examples that could look pretty similar that could like potentially keep them separate, but they're actually not separate. So they're actually under the same class. So within class imbalance problem is that. And this algorithm uses, again, k-means clustering technique. What it's doing is that it's taking a random set of k examples for each cluster for both majority and minority classes, and computing the mean feature vector for these examples, which is designated as a cluster center. So I think the image is here. It is here in a way. I think it is the example for one of the next technique, but the idea is the same. So like you are basically firstly, you're firstly basically taking just like few points, calculating the Euclid distance between those points, and then sorry, it's k-means, it's not Euclidean distance. Yeah, I'm confusing it. So yeah, so remaining 10 training examples are presented one at a time. Okay, it is taking a set of k examples for each cluster. So set of k examples, what I mean by that, let's say I'm taking this cluster. If I take set of k examples, in this case, k equals to 3. So for these 3 points, we are taking the mean of these 3 points, which is denoted by this triangle CA. So that is the mean of this cluster. And then what it's doing is that next, the remaining training examples are presented one at a time for each example. Then the Euclidean distance vector between it and each cluster center is computed. So this next step, let's consider just this and this. So this is introduced here. Then the Euclidean distance between this point and this point is calculated. Then okay, so I think that is trying to say is that each training example is then assigned to the cluster that exhibits the smallest distance vector magnitude. So let's say between this distance and this distance, whichever is the smallest, this x3, I think is an x2, sorry, it goes here. So looks like this is the smallest, so it will go here. And as you can see, it looks pretty similar to this, so it will obviously go here. But like without visualizing, you won't know if it is actually the same. But essentially, k-means clustering is doing that. Okay, so let's see. So lastly, all cluster means are updated, and the process is repeated until all the examples are exhausted. So once this happens, it moves to this, then it creates the average of those 4 points, and then creates a second, as like another mean, and then like it kind of is doing it iteratively until we have all our training examples under one of these clusters that are available here. So, okay, I think I kind of mentioned that. Yeah, I think the example is already given there. But then it's doing a lot, it's doing a bit more than that, which in this case, so I'm just going to quickly read and then we're going to go through this. The original, yeah, okay. Yep. Yeah, so in here, once that all examples are exhausted, the CB algorithm inflates all majority class clusters other than the largest. So this is the point where it is doing something different for an under unbalanced problem. Like in normally k-means clustering won't do that, but for this problem, what it's doing is that once this procedure happens, these majority class examples, so these three clusters, they are all majority class example cluster. The largest cluster among this is A. So this B and D would kind of oversample till the point they reach the same number as A. That's what it's essentially saying here. Out of all the, so yeah, let's go to this. That's what it's saying. So all the majority class clusters are the same size as the largest. And then what is doing it for undersampling, right? So, sorry, what is doing it for the minority class? So for the minority class, it is oversampling it, obviously. But how is it oversampling it? It is taking the number of, so this number of data points in the majority cluster after oversampling the majority cluster as needed. And then it is dividing it by this value, which is m-min. In this case, m-min denotes how many clusters for the minority class examples have been created. So as you can see in the image, for the minority class examples, we have these two clusters. So that m-min is 2 in here. So the total examples will be 30 for this procedure. The final data set has a stronger representation of rare concepts. So as you can see, when that happens, after all this process, minority class examples are also increased significantly, as you can, and that's what it's essentially saying. So see, there's so many of them. Yep. So even though they were rare initially, after doing a clustering this way, we have a lot more minority class examples to learn from. And in empirical results, whoever experimented with this process have said that it has worked with the problem of targeting the within class imbalance problem, or with between class imbalance problem to come up with an effective strategy for handling an imbalanced data set. Next up, we have something called a mode boost. So what this mode boost is doing is, let's see, just quickly go through this. Each successive classifier and some of its more minority classes, each Yep. Okay, so mode boost. Okay, so the boosting algorithm is really applying mode plus the boosting algorithm, like the concepts of boosting algorithm. And what boosting algorithms does is that it is learning. So each time it is a tree-based algorithm, firstly. Secondly, it is not sequentially creating the trees. It is creating the trees separately. And while it's creating it, is at each level, it's calculating, like it's doing a majority voting. After voting, wherever, in whichever tree, at a specific level, at whichever point, the information, there's impurity in a way. Impurity meaning that at each level at a specific node, if there's a mixture of majority minority class examples, means it is impure. It hasn't found a way to separate the majority minority class, means it hasn't been able to classify it at that level. So it will start growing from that level, that tree. That's kind of boosting, like that's kind of the principle of boosting. So it is basically saying that each successive classifier, so in this case, each successive classifier ensemble focuses more on the minority class. So by combining boosting and smote, it is actually focusing more on the minority class example at each step, so that whatever it couldn't learn before, because minority class examples are hard to learn because we don't have that many samples for minority class, it can actually learn from it iteratively well using a boosting technique. So yeah, it's basically saying since each classifier ensemble is built on different sampling of data, the final voted classifier is expected to have a broadened and well-defined decision region for the minority class. So that's like smote plus a boosting technique. And I think it is also used. It is not used as much as smote in general. Like obviously, people usually start with the simplest, which is the random. But random often doesn't do the job. So then you kind of move in the complex territory, and now we're going to the complex territory in playing with the data when there's this kind of problem exists. And this data boost algorithm, I think it's a bit complicated. So let's just go through it a bit slowly, I'd say. Give me a moment. I'll just bring something up for that. Yep. Okay, cool. So Data Boost IM. What it's doing is that it is applying a technique from adaptive boosting to achieve high predictive accuracy for the minority class without sacrificing the accuracy on the majority class. So the difference between this and the previous one kind of just focuses on getting the minority class right. But we don't quite know if the majority class examples are also having a better accuracy or not. But in this technique, it kind of ensures that. And how, right? So what it's doing is that first it generates those fake samples, like synthetic fake samples according to the ratio of difficult to learn samples between classes. I think there are formula that will say how it does it. So let's read it line by line. So in this case, again, the notations are basically saying is that S-min is the minority class examples, S-major is the majority class examples. There is something called a weighted distribution DT. It is representing relative difficulty learning for each example SXI that belongs to S. So these X's, okay, we rank these Xi's in a descending order according to their respective weight. We then select the top S times RT examples to populate the set E. So this is like we're selecting a random point from our subset of samples. It could be a majority class, it could be a minority class, we don't know. But then what we're doing is that we're ranking these X's in a descending order according to respective weight. And then we're selecting the top S times error examples to populate this. Okay, there's a different set that we're creating. So we're taking those S's. If you're struggling to find whether they're a majority or minority class, the ones that we are struggling a lot, we are taking them out, and then we are putting them in another set called E. It's saying that this error rate is the current learned classifier. So it's the error rate of the current learned classifier, means it's quite high. If it's selecting it from top down, descending order, this error rate is the ones that has a very high error rate, they are going under this set E. So yeah, it's basically, that's what it's saying here. So it's a hard to learn samples for both classes and has subsets E min that belongs to E and E major. So again, because we don't know what they are, hard to identify, classify, we still don't know whether a majority or minority. They could be either E min or an A major. And it is kind of is saying something obvious, because obviously our majority class examples are much less. Our minority class examples are much less than our majority class examples, and that's why it's saying like majority class examples. Actually, I think they got the notation wrong. So I think, yeah, it's that's what it's saying. It's expected that. Oh no, that's fine. That's fine. Yeah. So because we don't know, even if we don't know what E, like what this E whether it's an E min or E major, but because we don't have that many minority class examples in our data set, that's why we're expecting that we will have more minority class examples in this subset E than a majority class examples. And then what this is doing after that, once those examples are identified, like the set of E is created, then it's going to create a synthetic sample, like those fake samples, according to two-step process. Firstly, it is identifying a seed from E, and the seed is being calculated here. So we'll just go to that. Yeah, so it's saying that from E, which is from synthetic samples are formed, and generate synthetic data based on these samples. So yeah, this is the seed identification process. It's based on a ratio of class representation in E and S. So for majority class, the seed is ML, and the value of ML will be the smallest of this ratio, the sample of majority class divided by the sample of minority class, or whatever E major we have. Like take the smallest of these two. For minority class, similar, but because we have the majority class seed, we multiply it here because we have a bit more information. Then after that, there's another step right after that. So this is the second step. Once we identify the seed, we then proceed to generate the synthetic set. Now we're processing the synthetic set, where this set, like anything that is a minority class belonging to the synthetic set, yeah, it's just basically essentially saying the same thing as this, but in this case, they will belong to the synthetic set. Such that, yeah, so in this case, how do we calculate these, right? This will be calculated by taking the seed for minority class seed and times it by S min. Excuse me. And same for majority class, just the same calculation, but for majority class. Then our original set is augmented by this E synthetic set to provide a more balanced class distribution with more new instances of the minority class. Last step is the weighted distribution dt is updated with consideration to the newly added synthetic steps. So it's a long process, this algorithm. I haven't seen this being used anywhere, to be honest. So I think it was just done very empirically, but in practice, barely seen this being used. Okay. I mean, they're saying that these sampling methods are effective in dealing with learning from balanced data. That's quite strong. Blah, blah, blah. And let's just go to this quickly. So yeah, it's just talking about the benefits of this, which I'm sure you can read. I mean, it's not that complex to understand here. There's another algorithm that's mentioning it here. What this is saying is that it's not really computationally heavy. This juice boost, I think it's juice boost, I'm not sure. But what it's doing is that it's applying the same principle of random oversampling, undersampling. But instead of just doing random oversampling or undersampling, whatever it randomly oversampled or undersampled is kind of moving them a bit. Like it's moving, let's say if there's a point, if in a minority class example, there's a data point called X that is randomly oversampled. Let's say it's called an X hat, but then it's probably adding something to it. Let's say it's adding a plus minus 0.5. That's what it's really doing in this case. So what it's doing is that while it's doing that, it's making sure that those noise that is created is independently and identically distributed. So it has like a similar probability. So identically distributed, that means like it has the same probability to be selected no matter what. But yeah, it is essentially saying is that it is pretty time, like it saves the computation time that may take somewhere like a data boost. Sorry, 1 second. I think that was the end of the sampling from a data point of view. But the next step, okay, there is another way we can tackle the problem of unbalanced data set. In this case, it has nothing to do with data. It has everything to do with playing with the model. And in this case, the playing with the model is really playing with the cost function of the model. So any machine learning model you will work with, or if you have ever worked with, I'm sure you would know, whoever worked with it, it is reliant on a cost function, which is ensuring what penalty you should give the model isn't doing well. So that is the main principle it's working on. What it's doing in here is that it's a cost-sensitive learning method. It's considering the cost associated with misclassifying the example. So yeah, anything that's been misclassified is putting a penalty on it by using different cost matrices that describe the cost from misclassifying a particular data examples. Let's just look at what this is doing here, right? The cost-sensitive learning framework. Yeah, so what I was just mentioning, that it is kind of putting a penalty on classifying examples from one class to another. I think this is kind of important to understand for this problem. So this C min major is the cost of misclassifying a majority class example as a minority class example. So the true class in here is the majority class, but this is actually identifying as a minority class. So that's the cost of it. And what it's also saying is that given that it's an unbalanced problem where minority class examples are low, cost is always going to be higher for a minority class examples being misclassified as a majority class example. So it's always going to be higher, which I'm sure it's very intuitive. You would understand why, because these are going to be hard to identify. And that's why we're potentially going to have more cost in identifying these minority classes. That's why this cost is higher than this. And we're probably not too much worried about this anyway. So yeah, I'm just gonna quickly go through it. And if you have worked with Bayes' rule, you probably remember what this formula is trying to say. So what it's basically trying to say is that it is putting a conditional risk here. So in this case, J is the minority class. It is being misclassified as a majority class. I is the majority class here. That's the cost. And let's say this is the example that is trying to be classified either in a minority or majority class. So let's say, given this example, what is the probability that this example is being, that this example had a probability of being under a minority class? But the risk of doing it wrong is being identified using this Bayes function, Bayes conditional risk. So I'm just going to go through this quickly, conscious of time. I do want to cover some things on section 5 before we actually can conclude the session. So what this is saying is that, so there are 3 categories of these techniques this paper is mentioning. It's a cost-sensitive bootstrap sampling approaches. And again, same principle as bootstrapping decision tree, but in this case is you playing with the cost function. So where misclassification costs are used to select the best training distribution for induction. This one is talking about, this is the second approach, is talking about cost minimizing techniques to the combination schemes of ensemble models. So this one is talking about just creating a bootstrap decision tree, but this one is trying to, this one is saying is that you're creating multiple models and you're then ensembling, combining them later. I'm just going to quickly go through this because this is essentially saying similar things. yeah, so this is what I want to talk about as well, just very quickly. And as you can see, this is a cost function. So it is kind of an adaptive boosting that we mentioned before. So adaptive boosting, it is a sequential creation of decision tree, which is learning information from the previous tree and feeding it to the subsequent tree as it keeps growing down the line, like down. And finally, stops when all the leaf nodes are pure, which is it doesn't have any entropy or the Gini coefficient is low. In this case, so these are just 3 variations of adaptive boosting function, but the main function is really this. So let's just understand the main function and the rest would kind of make more sense. What this is trying to do here, this is like a distribution function. Again, the distribution will be between a 0 or 1. And this distribution function is being created in an iterative basis. In here, this t is the total number of iterations to create this distribution function. But let's say at an iteration t plus 1, where it's like at the t plus 1 step, this is our function. So what this function is doing is that it is taking the function for the previous one, the distribution function from the previous step, and is timing it with an exponent of this whole thing. What this whole thing means is, this is, okay, in a scientific term, it's called the Euler function, I think. That's what a decision tree actually works on while it's trying to grow down the line. So in here, this alpha t is the weight updating parameter. All you have to do is eta t is the error from the previous step. So this is something that will come in the model, and you can play with it. This hdxi is the prediction output of the hypothesis ht on the instance hi. So in this case, don't worry about the word hypothesis, just consider it as the previous step of the tree, like of the forest, not the tree, the previous tree. Let's consider it as the previous tree. But this xi has been already predicted. We know the output of this. Et is the error of the hypothesis ht. So like obviously there is an error in the previous step. That's something we're trying to minimize here. And then zt is a normalization factor. Again, because this is a distribution function, we need a normalization factor so that we have the values between 0 and 1. Yeah, that's basically saying that this distribution function value has to be equals to 1. So this, with this description in mind, cost factor has been applied. So all it's trying to say is that you can do it in a different way. You can do it, you can either create, so see the cost function came in, ci. So you can put it in here or outside the exponent or somewhere else. So that's just a different variation of those ADA C1, C2, and C3. These are the 3 variations here. So this is the ADA C1, where this cost function is inside. ADA C2 cost function is outside. ADA C3 cost function is in both places. So yeah, it's just trying different variations to create the cost function and see how we can balance the data set. And what this found is that while you do that, it imposes a bias towards minority concepts and also increases the use of more relevant data samples in each hypothesis, providing a more robust form of classification. So saying it's imposing bias towards minority concept, bias is not a good thing, obviously, but in this case, it is good because we want to learn those minority concepts better because those examples are limited. Again, same thing as the paper is mentioning. It is kind of the same function, similar concept. You can just go through it. So all it's trying to say is that if you want to change the sign, like there's a tweaking parameter, introduced a hyperparameter, which you can tweak to kind of change the distribution of the balance of your data set here. Okay, quickly. Sorry, I'm skipping a lot, but all I can say is that these are all the cost functions. So this is just trying to talk about the decision, like same concept as we mentioned, just different variations. And this simply is just talking about how it's been applied in a neural network, and it's kind of like, again, like I said, it's a diction. This paper is a dictionary of a lot of things, so it's going to be very hard to cover everything, but we can just quickly cover a couple of things. But yeah, again, this is just a cost function for a neural network or deep learning problem. The same principle. I will quickly go through this. I'm conscious that we are almost getting pretty close to the time. I probably will take a bit more if that's okay. But yeah, just 2 minutes, I'll run through this, and then we move on to the next step, which will be pretty quick because it's easy to understand, and a lot of concepts they are pretty prevalent. Like, they're not hard. This is a bit like tricky. This kernel-based learning framework. This is another way you can tackle the problem of unbalanced data set. And all it's trying to, like, kernel-based problems are basically, what they try to do is that they try to create a plane to classify, for a binary classification problem, I should say. Multi-class, yes, exists, but let's say in this case, for a binary classification problem, it is trying to create a plane to separate majority from minority class, which sometimes, like, you probably have to inflate the plane. So if it struggles to separate them in a 2D plane, like an X and Y plane, it creates a 3D plane, which it easily can separate. So those overlapping problems between majority and minority class doesn't exist in a higher plane, which could exist in a 2D plane, which this kernel-based learning framework can solve. So yeah, the support vector machine, that is one of the most famous kernel-based learning algorithm. There are others too, but this one is the mostly applied and used. And yeah, it's essentially saying it's just creating a constant boundary, which is called a support vector. And it's trying to minimize the separation margin. So support, okay, I wish there was an image. I wish there is something. It's very hard to explain without an image. Yeah, so okay, the image is here. So this is the support vector, yeah. And these two are those soft margins. So all it's trying to do is that it's trying to separate the majority class from a minority class by kind of finding that optimal plane that could separate those two classes. The reason I'm not, like, obviously, firstly, short of time. Secondly, I haven't seen much application of SVM because decision trees are actually really good at so many problems. So I haven't seen much application of SVM in, like, tackling unbalanced problems. So I think there are some empirical research here, which is great. It's done some cool things, but in practice, I haven't really seen much of this. I'm just going to be very quick. So just going to go through this, some examples that it's trying to talk about the SMOT with this different cost method. So it's trying to create cost function from an SVM support vector and combining with a SMOT, and then again ensembling problem, then over undersampled SVM. Like, it's just doing various things with SVM with ensembling, SVM with SMOT, SVM with random undersampling, oversampling. It's just doing a lot of things here. This one is quite interesting. I found what it's trying to do is repeatedly undersampling the majority class using a support vector machine. That's all it's doing, but in a way that it's doing it in a granular way. And by granular, I mean is that it is picking some examples of majority class, combining it with a minority class, creating a support vector, learning from it, then create whatever it learned from, it's discarding this majority class, and it's just doing it repeatedly till it can actually, like, separate those two different classes. So as you can see, it's basically there's a distinction between local and global. So what it's saying is that these negative local support vectors are formed to negative information granule and removed from the original data to obtain a smaller training data set. So yeah, like it's kind of just like those are the majority class, and it's removing it by combining it with a minority class, doing support vector, and then just like eventually it's trying to come up with the perfect hyperplane to separate those two classes. These are all just variations of kernel-based methods. I haven't really seen much of these much elsewhere. This is good though. I think this is quite. I think there's a good paper on it too, so you can read it. But it is kind of what it's trying to do is just it's trying to kind of making training data a bit fuzzy. It's more like that juiced boosting that we talk about. It's kind of similar things it's doing, but with a support vector machine. Sorry, quickly go through this. These are just all variations of, again, different cost function. This is like active learning. This is basically combining different processes, all empirical study. Yeah, so, okay, very, I need to do very quickly because I know we're pretty over time. But this one, I know this probably, a lot of you already know this, but let's just cover it because these are actually quite important. Even though we know, I feel like from what I actually saying, even though we know these concepts, we still, a lot of us haven't still applied, like really unraveled the strength from using an accuracy or FP, like TP, false positive to true positive precision recall. We haven't really used them well, but this has some good guidelines. So let's just go through it quickly. So accuracy is basically, I think in week 2 there was a session. So I'm sure a bit of this has already been covered in that ROC analysis session. Same thing in here, but for an unbalanced data set perspective. So if you want to find the accuracy of a model, you get the values that are all like true positive, which is like all the positive, in this case, let's say minority class. So all the minority class that the model also has predicted as minority class. True negative in this case is that all the majority class that the model has predicted as a majority class. And these are all the examples in the sample set. Error rate is 1 minus accuracy, just the opposite. This is quite easy to understand, but what it's essentially just saying is that for an unbalanced data set problem, accuracy is probably not going to be a good metric because it is going to pick the majority examples pretty well all the time, but minority examples might be missed out. So if it's got a 95% accuracy, it is probably going to pick all the majority ones 100% right, but those 5%, it probably isn't picking those minority samples right. So in this case, when we have an unbalanced data, accuracy isn't probably the best thing to go with. And yeah, I think this is very important, which I'm sure we all apply if you do, like if they're in data scientists on the call, even analyst or ML engineer, whoever, like even researchers, we all apply these. But essentially, I think where playing with unbalanced data comes with is tweaking with this F measure. I feel like, because this F measure, like I think in industry example, everyone talks about it as a harmonic mean. And why is it harmonic? No one really talks about it. It's just trying to like find a harmony between the precision and recall by using this parameter called beta. And this beta, you can play with it. So when this beta is 1, it is called the F1 score. And I think this is quite intuitive, but I found a lot of people don't know. So I just thought I'll mention that. When this beta is equal to 2, this is called the F2 measure. And when this beta is equal to 2, it's actually putting more weight on recall. Yeah, as you can see. So it's timing the recall, it's making the recall higher. So in a case when there's an unbalanced data set recall, we want to pick, like we want to have a complete picture of all the minority class. So recall is probably be more important to get right than the precision or an accuracy. So if you want to play with an unbalanced data set, you probably should play with this F measure. Maybe F2 is a good score, or you can tweak it. Like you can pick various values of beta till you get your recall 100% right. So this is what I think this is quite important to understand. And in an imbalanced data set case, this is quite widely used. This G-mean is basically a geometric mean. It's just taking a square root of sensitivity and specificity. Sensitivity in this case is true positive by true positive and false negative. Same thing as recall. So sensitivity, recall, same thing. Same thing. Like recall is also the same thing as true positive rate, as you can see here. Okay, quickly. Excuse me. ROC I'm not going to cover because it's been covered in week 2. I think there are recordings out there, so I'm not going to cover that. But what I'll cover is a bit briefly before I finish after the cost curve is the precision recall curve. And this is important for the unbalanced data set problem. What this is saying is that in a case of highly skewed data set, and highly skewed is majority class high, minority class low, it's observed that ROC curve may provide an overly optimistic view. Yeah, obviously, it's just looking at accuracy. And in this case, the PR curve can provide a more representative view of the performance assessment. And how do we do that, right? So it kind of does it using this formula. Let's just, sorry, that's the cost curve formula. But it is kind of shown here. So what you can see is that, okay, it is kind of doing it as a true positive rate on this axis, false positive rate on this axis. And you recall, true positive rate is recall. So if you want to get recall right, recall 100% right, we probably should focus more on getting, like, this is probably going to be our optimal line for an unbalanced data set. So yeah, what it's essentially saying is that, yeah, I'm just going fast. So it's not distribution dependent, almost superfluous, because session-based solar recall is equivocal. So recall provides no insight. Anyway, like, it's just talking about the problems on some problems this may have. But yeah, it's just basically trying to say is that this L2 ROC curve provides a larger AUC measure compared to the L1, therefore corresponding classifier associated with curve L2 can provide better average performance compared to the classifier associated with L1. So essentially, in a case where unbalanced data set exists, precision recall curve is the best thing to pick to assess the performance of a classifier classification model. Sorry, not that one. It's here. Sorry. Yeah. Yeah. Okay. It's here. Okay. So it's basically, that's what it's saying here. ROC curve will fail to capture this phenomenon. Precision metrics, on the other hand, consider the ratio of true positive with respect to true positive and false positives. This can correctly capture the classifier's performance when number of false positives drastically change. So we just want to be able to capture the classifier's performance, even if our false positives are changing. This PR curve is actually not perturbed by that too much. It can still do a good job. Cost curve, I think cost curve, you can like look at it with PR curve. I won't say just use cost curve, but it is kind of a good, like, intuitive exercise to kind of see how much cost you're incurring for getting the predictions wrong, or getting the like true positive or false positive rates wrong. So it's essentially, it's just putting a penalty, like, as you can see, it's adding false positive rate to this cost curve, and you know, so that it is penalizing things that it's getting wrong. Cost curve method plot. Yeah, so it's basically, it is represented by a probability cost function that is based on the probability of correctly classifying a positive sample. So this is the probability cost function. It is the probability of correctly classifying a positive sample. So it is timing it with anything that is, so it's 1 minus true positive. Everything that is right, it is taking that from here, and it's also taking the false positive, and it's timing it with the probability cost function. Like, it's just a function to penalize or find the cost of your precision recall curve. I know I went through this pretty quickly, But what I can say is that after this, it's just all like in under kind of just a story of what you can learn from it. What are the opportunities and challenges? And I think whatever I kind of found in this opportunity and challenges section, some of them don't exist anymore because this paper is almost 10 to 12 years old. Even though we use the concepts from here, they are kind of like some of the challenges have been tackled by some way or the other. So just like read it and see like how you feel about it. But yeah, there isn't really much. It's just asking few questions, and in here it's kind of just talking about all those assessment metrics from a multi-class problem point of view. Similar thing, but the summary here is just that making the multi-class problem to a two-class problem where keep one class as is and combine all the other class and do a classification on that, and then like do it separately in different folds and just combine it all together at the end. So yeah, I guess in summary, it's the rest of the paper is just talking about what are the opportunities and challenges next, and the conclusion that like it's nothing that needs explaining. It's just things that you probably can read at your own time. But yeah, I guess that's all I have to cover. I know I'm a bit over time, so probably not going to do a recap because this paper has been covered for the last 2 weeks. But if anyone have any question, please feel free to ask now, or if you don't want to ask now, please like feel free to reach out to me. If you can reach out to me on LinkedIn, I can try to answer, or even you can email and I can answer later if you have any questions.
So, thank you very much, Anki, for the great presentation. So any other participant who want to ask Anki for the question? So if not, may I ask one question, please? So what are some of the use cases in the financial sector applying this concept?
Yeah, because I actually worked on the sector, right? So I think the use case, pretty common are fraud detection. That's everywhere, right? And I think one of the current ones we have are like predicting if a customer could default on a loan. Especially if anyone is in Austria, they would probably know that our interest rates are going quite high. So that is impacting a lot of people with their home loan repayment. Like a lot of people are actually on the verge of defaulting. So we're kind of just trying to predict it, not from like a point of view that we're not going to support the customers, but we are trying to find in what way we can help those customers. So just kind of predicting it first, and then if you can, go back to them, ask them if they need any help from us, like just temporary kind of, like a stop, or that's beyond me. Like I obviously I don't make those decisions, but it's essential to help customers to understand, or like help us to understand who could be defaulting and how we can help them in the interim. So like that's one of the use case. Another use case is from like a customer kind of a churn problem. Obviously, that is an unbalanced data set problem for us as well in a way, because we don't have that many churns. Like not a lot of customers leave us, but the numbers are quite low. So, but we do want to keep track of people who may leave us. So for that kind of problem, we apply a lot of principles from this paper.
Yeah, thank you very much. So as I'm also doing some machine learning method, so another question I would like to ask you is about which of the undersampling and oversampling method have you found to the most useful?
Yeah, no, good question. I think just to, as a brief, I would say at a boost, adaptive boosting is actually something I think quite useful. And combining SMOT with some kind of ensembling is quite useful as well. those are the few ones I found quite useful. And in terms of evaluation, I think I was talking about tweaking with F-score. That is definitely something I would like to highlight here, because that F-score tweaking is it is quite common for us to do, so that we can get a good recall. So yeah, those are a couple of things that comes to my mind. Obviously, we start with the easy random sampling, and then we go down deep when it's necessary.
I see. Thank you very much. So is there any final question from Angie? Do you want to ask? You can also contact after this session to Angie directly. So if not, thank you so much, Angie, for your presentation. So thank you very much, everyone joining the week 6 session. Yeah.
Thanks so much, Sue. Thanks for the support, and yeah, hope it is helpful as to someone. I know it's a bit quick, but yeah, I really enjoyed covering this. So I hope you learn from it, like learn something from it.
Yes, thank you very much.
Good. Happy weekend.
Yeah, happy weekend. So as